Another shortcut is the SSS, or side-side-side similarity theorem, which states that if the corresponding sides of two triangles are proportional, then the two triangles are similar. Or look at this little drawing. If we have two triangles like this, and the side lengths are 8, 10, and 12 for one triangle, and for example 4, 5, and 6 for the other, and we take the ratio between the largest two sides, 12 and 6, then the next largest two sides, 10 and 5, and the shortest sides, 8 and 4, we get a ratio of 2 to 1 for all three pairs. They are corresponding, proportional, and therefore the triangles are similar. Let's look at these examples. Verify that triangle ABC is similar to triangle DEF, and then find the scale factor of triangle ABC to triangle DEF. When we say verify, we just mean show. Show that it's the case. We don't have to prove anything. It is the case, but we have to show why that is. So using our side-side-side similarity theorem, let's make the ratios of the respective sides. The largest side of 33 over 44 will give us a ratio of 3 over 4 simplified. The next largest, 21 over 28, ends up in a ratio of 3/4 as well. And the shortest sides, 18 over 24, also end up in a ratio of 3/4. So the ratio is the same each time, so we can say yes, they are similar, and the scale factor is the ratio that we just calculated. The scale factor is equal to 3/4. So why don't you go ahead and stop the video here, and using our side-side-side similarity theorem, verify that triangle ABC and DEF are indeed similar here too, and find the corresponding scale factor. Hopefully you came up with the same results. Taking the ratios of the largest two sides, the middle two sides, and the shortest two sides, you get a ratio of 3/2 each time, and that is also our scale factor. Moving on, we can also determine which triangles are similar and which aren't. In this example, we have 3 triangles given, and we are supposed to determine which 2 of these 3 triangles are similar, and then find the scale factor for the pair of triangles that are indeed similar. So let's at first compare our 2 triangles here on the left. The largest sides, 24 over 18, give us a ratio of 4/3. Let's move to the next 2 sides. 20 over 16 gives us a ratio of 5/4. And these 2 ratios are not the same, so we can already stop working at this point, because these 2 triangles are not similar. Let's look at our first triangle and the last triangle. See if these 2 are similar. Starting with our largest sides, 24 over 30, we get 4/5. 20 over 25. We also can reduce this to 4/5, Now that's looking good, but we can't stop here. We have to make sure that the ratio is the same for all three pairs of sides. So we need to also compare the smallest sides, 16 and 20. 16 over 20. The ratio also can be reduced to 4/5. So indeed, these two triangles are similar. So we can state that triangle ABC is similar to triangle GHJ, and the scale factor is the ratio that we have found each time comparing two pairs of corresponding sides, and it is 4/5. There is one more shortcut, and it is the SAS, or side angle side similarity theorem, and that's kind of like a mixture of the previous two. And this is how it goes. If two pairs of corresponding sides are proportional and the included angles are congruent, then the two triangles are similar. And looking at a drawing, it would look like this. If we have two sides, and this one may be 8 units long, while this one is 4 units long, this one being 12 units long, while this one is 6 units long, and the included angles, the angles between the two sides that we have, are congruent, indicated by this congruence mark, then the two triangles are similar. Let's work through these last two examples. Is there enough information to determine whether these triangles are similar? If so, write a similarity statement and find the scale factor. And we are going to look at our first two triangles. We have two given sides. The larger of the given sides is 14 in triangle ADF versus 15 in triangle CRT. And the shorter one is 9 versus 10. And we also have an angle, or two angles that are congruent. Both angles have measurements of 72. But these two angles are not included in the two given sides. So we would have a side, another side, and an angle. Uh-oh, I have spelled a bad word backwards. We cannot do that in math. This we cannot use. This is not the SAS similarity theorem. So we have not enough information. So let's look at the two triangles in example 8. Here again we have them both overlapping. So before we get started, let's draw them separately so we can sort out the side lengths and all the information we have. We got the smaller triangle CDG, and it had side lengths of 15 and 20. And then we had the larger triangle CEF, with side lengths CE, which is 15 plus 12, that's 27, and CF, which is 20 plus 16, in other words, 36. So we are given two side lengths each, but are we also given the included angle, angle C? Well, looking back at our original diagram, we see that C is right here, and C is the same angle. So if it's the same angle, then it has to be congruent. Angle C is congruent to itself, of course, and that is because of the reflexive property. All right, we have a pair of angles that is congruent, So let's see if the sides are proportional. 15 divided by 27 is equal to 5/9 once we reduce it, and 20 divided by 36 is equal to 5/9 as well. So these two are the same. The two pairs of sides are proportional. We have two congruent angles which are included in the two given sides. So by the side angle side similarity theorem, we can say that triangle CDG is similar to triangle CEF. And remember, we're also supposed to find the scale factor. Well, we have found the scale factor. The scale factor is equal to 5/9. Circle both our final answers, and we are done. Good job. For your summary, I would like you to spend a few moments to answer the following two questions. Which triangle similarity postulates or theorems can we use? Have we learned about today in class? And what information do we need for each of them? All right, that's it for today, and I will see you in class.